Welcome back, Algebra 3. We're in Lesson 21. Let's talk a little bit about evaluating functions. So we know how to do that for the most part. We know that evaluating a function is basically just a substitution. So let's jump right into 21.1, and we are going to evaluate this function. If f of x is equal to x squared plus x minus 10, find f of 5. We remember how to do these. We just take the value that is given to us and substitute it in for all the x's here because we're told that's what x is. So f of 5 would equal 5 squared plus 5 minus 10. So 5 times 5 is 25 plus 5. That's 30 minus 10 would equal 20. So 20 is the value that we would find when we substitute 5 in for x. That's all we're doing. Let's do 21.2. So here we have another function. If f of x is equal to x squared plus 1, we're going to find, and this time we're given an expression x plus 2. So we do the same thing. Whatever is here, we sub in for x. So this would be x plus 2 squared plus 1. When we square this, we find that x times x is x squared, and then we have a 2x plus 2x plus 4 plus 1. Then we combine all of this together and we find that x squared plus 4x plus 5 is the value of this function. Easy peasy. Now let's go a bit harder. Let's do 21.3. Here we have some degree problems and some geometry mixed in with our functions. So if h of theta is equal to the sine of theta, find 4 times the square root of 3 times h of theta when it's 30 degrees. So the thing we have to do is know how to read this and know that this is all factors. So what we're really looking at is 4 times the square root of 3 and then h of 30 degrees. So we are going to sub this in for this theta here. So 4 times the square root of 3, and then we have sine of 30 degrees. That's what we're really doing. So in order to find the sine of 30 degrees without our calculator, we're going to remember our reference triangle that we had. We took an isosceles triangle that had 2 all the way around, and we found our values for it, right? So what we're going to do is we are going to remember where everything is. And this is our 90 degree, this is our 60, this is our 30, because this was our angle bisector, right, where we cut the isosceles triangle in half. The hypotenuse is 2 because we had 2 all the way around. And then that means that this was 1. This was our leg that was 1. And if you remember, I'm sorry, that's not our leg that's 1. This is our leg that's 1 because we count all the way around 1, 2, and then this is the square root of 3. And I remember that this is the square root of 3 because I remember 30 times 2 is 60, right? I also remember that this is the 90 degree angle, and 9 from the 90, square root of 9 is 3. So that is why it's here. The square root of 9 is 3, is how I remember that. So 1, 2, 3, if it helps you to remember that, in what order to place those. And this, remember we have the bisector here, it cut this base in half. Half of 2 is 1. So that helps you remember how to put that together. All right, so now we have our unit of reference. So first we have to find the sine of 30. And sine is so in SOHCAHTOA, sine is so. So that's the opposite over the hypotenuse. So the sine of 30, the opposite of the 30, the side opposite 30 is 1, and the hypotenuse is 2. So the sine of 30 is 1/2. So 4 times the square root of 3 times 1/2 would be 4 times the square root of 3 over 2. And that is going to be reduced. 4 divided by 2 is 2, so that is going to equal 2 times the square root of 3, and that would be your answer. All right, not so hard once you understand how it all goes together and what you're looking for. All right, so let's move on to domain and range. In the domain and range, we have to remember what they are. The domain is just your x values. All of the x values within a function, that's the domain. And the range is all of the y values within a function. So anytime you graph a line, or anytime you graph a parabola or a circle or whatever it is, you are looking for everything that could be a possible value of x and everything that could be a possible value of y for your domain and your range. So let's begin with 21.4. And we are going to look at this. It says that if f of x is equal to 10 minus x, find the domain. All right. So what is the one thing that a domain cannot have? Remember that the domain is the number line, and the number line includes all of the real numbers that are negative, 0, and that are positive, right? It's all of those. So it could be fractions, decimals, positive, negative, all the integers, right? All of those too. But it cannot be an imaginary number. We don't have those on the Cartesian coordinate system. There are no imaginary numbers on that system. So there's no way that we can graph it. So that means we cannot include values that would create imaginary numbers. So the lowest this can be, for it to be an imaginary number, it would have to be negative. So the lowest that this can be, this x can be a 10, and that's it, because 10 minus 10 is 0. If it's below that, if it is below 0, even a fraction, it's a negative number, and therefore it would be an imaginary number when the radical was calculated. So x is going to be greater than or equal to 10. That's our domain. Those are the values of x. So we would write that as the domain of f equals that x is a member of the set of all real numbers such that x is greater than or equal to 10. That's it. That is how you would write that. Okay. X can be a, I'm sorry. I read that backwards. That should be less than. Why should it be less than, Miss Tracy? Because if x is 11, it's a -1. So x can be a 9, x can be a 10, x can be a -14, but it cannot be an 11. It cannot be 10.1, because then we have a negative number as our value. So I got that a little backwards. I knew what I meant, I just wrote it the wrong way. So be careful. Reevaluate your work before you turn it in. Always double check it. And to double check it, all you have to do is sub in some numbers. So let's look at anything that's less than or equal to 10. 10 minus 9, square root of 1 equals 1. All right. Let's try a negative number in here. 10 minus -6. Well, that would equal +16. So that would be square root of 4. or square root of 16 would be 4. So you can use negative numbers, you can use positive numbers and get a response. That is a valid response. And you could even say 10 minus 10 is 0, so that value would be 0. The y value would be 0. All right, and that's what we're doing, is we're trying to find valid y values. So let's look at 21.5. This one's a little bit harder. If, that's not a z, I promise, it's an I. If g of x, I decided to name it something different, is equal to 1 over x minus 2. Find the domain of g. So looking at this, the only number that that x cannot be is 2, because then that is what would give us a 0 as the denominator. So we can't have that. We can't, because it would be indeterminate. We can't graph that at all, because every value of y would be indeterminate. There's no way to solve that. So we have to say that x cannot equal 2. Easy peasy. That's it. That's our domain. The domain of g is equal to x being a set of all real numbers, or being a member of the set of all real numbers, such that x is not equal to positive 2. That would be how we write that. No problems whatsoever. All right, so I think we're getting the hang of this. Let's move on to something a little bit more difficult. 21.6. Here we are going to find the domain and the range of this function y is equal to the square root of x. And then we're going to graph it. All right. So here's how we would do that. So we have our function here, and we need to find values of x and y so we can determine our domain and our range. So again, this is a radical sign. So we cannot have an imaginary number, because imaginary numbers do not exist in the coordinate system. So what we will do is we will figure out what is the lowest number that x can be. Well, it's a 0, because we can have the square root of 0. 0 times 0 is 0. We can logic that out, right? And then we can go up from there, but we can't have a negative number, because the square root of any negative number is going to be an imaginary number. So let's start with x is going to be greater than or equal to 0. And that looks right. So there's our domain. Our domain is equal to x is a member of all real numbers such that x is greater than or equal to 0. All right, there's our domain. Now, based on our domain, we have to figure out what our range is. And the only way to do that is to figure out, based on a series of numbers that we determine for x, what the y answer will be. So to do that, we're going to do our table. I'm going to just create this little table right here. Remember the little function machine that we used to use? It was kind of the same thing. We're going to use our function table. So we're going to pick some values for x that we can use mental math to solve for y, so we don't have to whip out a calculator every time. So I'm going to start with 0, because that is our lowest number. Always start with that to determine the range of y. Okay, always start with the first number it could possibly be, or the lowest number it could possibly be, so that you can determine where y begins. So if I put in 0 here, y is 0. All right, the next number that I know I can unsquare is 1, and that would be 1 here. The next number I know I can use would be 4. Square root of 4 is 2. And the next number I know I can use would be 9. And then the answer would be 3. So I could see that y is increasing as we go. It begins with 0. So I can actually go ahead and write my range. My range is equal to y is a member of the set of all real numbers such that y is greater than or equal to 0. Just like the x was, except we use y values. So now I'm going to graph this. And you can absolutely use your graphing calculator to get there, but I would prefer that the first, until you know what you're doing, you know how to graph it, that you try on paper first. Let's get it to where every time you do it, you know what you're doing, you know what it's going to look like whenever you graph it. You're just checking your work with the graphing calculator. Let's do that first, and then we'll get comfortable with actually plugging it into the graphing calculator to get our response. So our first point is 0, 0, and that would be here. Origin and origin. Then we have 1 and 1, which would be here. Then we have 4 and 2, which would be 1, 2, 3, 4, 1, 2, right there. And then we have 9 and 3, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, right there. So our function is going to look like this. That is our function. And we could check our work if that looks a little weird. I have a free graphing calculator that I use. And I am going to plug in, let's see if I can stretch this out a little bit. I'm going to delete that one. Let me enlarge this a little bit, and we're going to plug this in. Square root of x. All right, and now I want to zoom out a little bit and see what we have. So, zooming in, here we have, I'll zoom out just a little bit more. All right, so here we have 1 and 1. Zoom out one more time. Here we go. We have 0 and 0 is our beginning, our y-intercept. Then we have 1 and 1. And then we have 4 and 2. You see the 4 and the 2. And then we have up here 9 and 3. So you can see the points we found are mimicked on this graphing calculator. So we know we found the right points. We know we did the work correctly. So that is how you would do that. All right, use your little table and use what you know about mathematics in order to solve. Pick appropriate numbers so that you can do the math in your head, and then you can check it on the graph to make sure. All right, so let's do one that's a little bit, well, it's a little bit more of the same, maybe a little bit more complicated, but it's the same type of thing. 21.7, and we are going to find the domain and range of y is equal to the square root of x plus 4. And then we're going to graph it. All right, so right away I see that x, if we have x as greater than 4 or greater than negative 4, how do I say that? Less than negative 4, that's what I'm looking for. If x is less than negative 4, we're going to get an imaginary number. But it could equal negative 4, and that'd be fine, because then it would be 0. Negative 4 plus 4 would be 0. So that's okay. So we can write the domain right away. I'm just going to write the capital D here for the sake of expediency. Domain is equal to x is a member of the set of all real numbers such that x is greater than or equal to negative 4. And let me show you why. If I have negative 4 here, then that's going to equal the square root of 0, which is going to equal 0. If I have greater than negative 4, and this is something you have to wrap your head around a little bit, the way to write this, greater than negative 4 as the number here gets bigger, it's actually getting smaller. So greater than -4 would be like -3. That would be the square root of 1, which would equal 1, right? Easy peasy. But if I went the other direction, if I went less than -4, then that would be, let's say that'd be -5 plus 4, which would equal a -1. Well, then that is going to be equal to 1i. That's an imaginary number. So we can't have any negatives. So that's why x has to be greater. This is the greater, and this is the less than. This is the equal to. So this one's okay, and this one's okay, but this one is not. All right, so you see how that works. Okay, and it's okay to test out some ideas to see what that's going to be. All right, you're checking your work right here. So now that we have the domain, I'm just going to erase this right here. Just know that you can check it. Just do some little scratches on the side and figure out what it is. I'm going to go over here to this. So if this is our domain, we're going to use it to find our range. So here's my little table down here. Here's my x values, here's my y values, and here is my my little table. So it's the square root of x plus 4, and I'm going to start with the very first number always that x can be. The lowest number it could be is -4. So if I sub that in and I say -4 plus 4, well, that's going to be 0, so y is 0. So now I'm going to just contrive to make these easy to solve. So I'm going to say 0 is my value for x. 0 plus 4 is a positive 4. Actually, I think I'm going to take that back. I think I'm going to do the next one I can do is -3. So -3 plus 4 is going to be a positive 1, and square root of 1 is 1. Now I'm going to do 0. 0 plus 4 is going to be square root of 4. That's going to be 2. And then I'm going to do 5. And that's going to be 5 plus 4. Square root of 9 is 3. So I contrived this a little bit just to make it easy to do in my head. It doesn't matter. I'm just picking points along the way to make sure that I'm graphing that line in the right direction. But this tells me my range. My range for y, because this was the lowest number that I could use, my range for y begins at 0, and it goes up from there. So my range is equal to y is a member of the set of all real numbers such that y is greater than or equal to 0. Because it started at 0 and it goes up, it gets greater than 0. And now we're going to graph that. So I'm going to put my lines here and right about here. Let's switch colors to make it easy to see. So my first point is going to be -4 and 0. So that's going to be 1, 2, 3, 4 on the 0 right there. My next point is -3 and 1. So 1, 2, 3 and positive 1 right there. My next one is 0 and positive 2. So 0 and 1, 2. So our y-intercept point is this right here. And then 5 and 3. So 1, 2, 3, 4, 5, 1, 2, 3. And this is what my function is going to look like. Just like that. And I can check that to make sure I did all my points right. I'm going to delete this one, and I'm going to type in square root of x plus 4. So square root of x plus 4. And then enter that. And let me zoom out so we can see what we have. So here we are. We have 4 and 0. That's that first point, 4 and 0. Our next point would be -3 and positive 1. We did that. Then our next point is the y-intercept of 0, 2, which we found. And then our next point was 5 and 3, which we have that one here. You can see how it goes from this point up to the next line, 3. So we did it correctly. We can check our points that way and make sure that we are graphing it right. It looks right here. I didn't quite get that through that point, but we get the idea. So that's how you can check your work with a graphing calculator and make sure that you understand what you're doing. All right, so next we have one more. It's a little bit more difficult because there are two conditions. So let me show you what that is. This one asks us to find, this is 21.8, and it asks us to find the domain and range of the function. And here's the function, f of x, such that the square root of, not 8, hello, x divided by x minus 2, or such that, equal to. I don't know why I said such that. The domain f of x is equal to the square root of x divided by x minus 2. So there are two variables here. So that means we're going to have two conditions. Our first condition is that x cannot be less than 0 because it can't be a negative number because it's a radical. So x has to be greater than or equal to 0. Right? So why would we say greater than or equal to 0 instead of greater than -1? Because there are values between -1 and 0, like -1/2, -0.25. We don't want those. We want to start it at 0. So equal to 0, greater than or equal to 0 is the right way to say that. Down here, we know we can't have a denominator that is equal to 0. It can't happen. So the only thing that gives us that is if x is a positive 2. Then that equals 0. So we can't have that. So x cannot be equal to positive 2. Those are our two conditions. So we'll write our domain as such. The domain of f is equal to x being a member of the set of all real numbers such that x is greater than or equal to 0 and x is not equal to 2. All right, so there's our values. That is how we're going to set up our table. And that's what we'll do. We'll start, we've got our x here, and I like to do this in black. I don't know why I didn't switch back over. Here's our graph, or our table that we're going to graph from. And square root of x and x minus 2. And then this is our y values over here. So remember, x can be greater than or equal to 0. So I'm going to start with, that's our lowest number. I'm going to start with 0, and I'm going to sub it in everywhere. 0 and 0 minus 2. So that would be 0, right? Square root of 0 is 0. There's nothing there. It doesn't matter what the denominator is. 0, 0 is where it starts. So that's our first point. So now I'm going to sub in, let's try 1. Square root of 1 over 1 minus 2. So we have square root of 1 is 1. So it'd be 1 over -1. So it'd be a -1. Right? Okay, so now let's try, we can't do 2 because x cannot be 2, though we're being told what numbers to pick. So let's try 4. I'm going to sub that in. Square root of 4, and then 4 minus 2. Okay, well the square root of 4 is 2, and 4 minus 2 is 2. So 2 over 2 is just going to be a positive 1. Okay, how in the world, I know what you're saying, I know what you're thinking, how in the world can we go from 0, 0 to 1, -1 to 4, positive 1? How does that line up? It does not. And I will show you why. Let's graph it. So we know that x cannot be, it cannot be 2. So that is off limits. we draw our little line like this. We cannot have x be equal to a negative 2. So we start with 0, 0, that's our first point. And then we have positive 1, negative 1 right here. And that goes like this. Because we can't go any further. That's all we can do. But then we have, this is 2, 3, 4. We have 4, positive 1 here. We need some more points this way. So let's do some more points this way. I'm going to add to this. Let's do 9 because I know I could find the square root of 9 easy. 9 minus 2. So then that would be square root of 9 is 3 and 9 minus 2 is 7. All right, let's try 16. Square root of 16 and 16 minus 2. So that'd be 4 over 14, and that would reduce to 2 over 7, right? So 9, let's see, 9 and 3/7, that'd be 1, 2, 3, 4, 5, 6, wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 3/7 would be about right here. And then we have 16 and 2/7. So that would be out here somewhere. 10, 11, 12, 13, 14, 15, 16, and 2/7. So this one would go this way. Just like that, I think. Yeah, it would go, it actually would go like this. Because over time, we're going to swap. This is going to get so small, we're going to have to swap the numbers. And start picking, we could pick small numbers. We can't pick 2, but we can pick other numbers here. That would make that go up. So let's check our work and see what we got. Let's check our graph and see where we're going. I'm going to delete this. And then I'm going to type in square root of x divided by, let me back up. Nope, I haven't typed this in yet, so let's see. Square root of x space, okay, I pulled out of it that way, space, divided by, that is not working, so let's do divided by, there we go, square root of x. I can put that on top now. Now I can click down here and say x minus 2. All right. So f of x equals square root of x, x minus 2. So I got my fraction format first, and then I put that in, which is what I probably should have realized. And I'm going to back this up a little bit. Let's minus this, zoom out, so we can see what we have. And we can see that we have all the y values possible. It's just that x cannot be equal to 2. We have all the negative y's and all of the positive y's, except for, and actually it comes all the way down. If we keep going, it does eventually, I mean, it hits on 0 at some point. I wonder if it goes down any at all other than that. No, it looks like a 0 is as far as it goes on the x-axis. So it does come back down to 0. However, here, x cannot be 2. It never touches the 2. It gets really, really close. And we can tell by zooming in. You can zoom in on this as much as possible. And you see x never actually touches the 2. It just stays right alongside of it. It gets really close, but it never touches the 2. Same thing on the other end. If I can get down here, X is going to get really close to the 2, but it is never going to actually touch it. It's never going to actually overlap it, right? So we back up, and that is what our domain and range will look like. So that what that means for our range is that the range of f is equal to y being a set of all real numbers such that actually that's it, because y can be anything. That's our range. Range is a member of the set of all real numbers. There are no stipulations on y because it can be negative, it could be a fraction, it could be positive. It's the only stipulation is that x cannot be 2. And we could keep solving and keep solving, but our graph on the graphing calculator shows us that this is the only condition that we can't cross. So, let's talk about types of functions now. So you see the benefit of having a graphing calculator, right? You can get started on your graph in the right direction and kind of get an idea of how to do it from your table. But to really drill down into the graph and to see your range, sometimes that graphing calculator is going to save your hiney from having to do multiple table calculations to double check and make sure your values are true. Instead, what you need to graph it for your homework, you're going to need to do some, maybe 5 or 6 points, especially if it's something like this. But this is what this would look like when you have a number that it can be any other number but this one, right? When you have 2 conditions, then you may end up with 2 different, lines that go here. All right, but you can always use your graphing calculator to give you guidance on that and to help you with that, which is the whole point of having a graphing calculator app. And again, the places to go and look, you can get Desmos is an app on your phone. You can have Desmos.com, which is a good one. There's also the GeoGebra suite, and that is an app that you can download to your computer, or you can do GeoGebra.com. That's also another graphing calculator. My favorite graphing calculator for my phone is Desmos, and for my computer online is Desmos.com. I like it better than GeoGebra.com because it's a little bit easier to use. It's very straightforward. GeoGebra, however, is the only suite for the computer that you can download to your computer and not have to get on the internet to use. Let's say you don't have the internet that day. You can use this without having to hit the internet. So that's the benefit of having that. Otherwise, I would use Desmos.com or Desmos on my phone. They're just better. I will add that on the ACT, you cannot use your phone. Your smartphone will not be allowed. So you cannot use Desmos on your phone. So you might want to invest in a graphing calculator for the ACT. Honestly, I wouldn't. What I would do is I would try to find somebody who's already bought one and is using it and borrow it. Figure out how to use theirs. Borrow it for long enough that you can use it readily, and then give it back to them. Don't spend $120 on a calculator that you're only going to use that one day for the ACT, right? Or maybe your parents will invest in a graphing calculator for the entire family to use whenever they need to take the ACT. And the rest of the time, you can just use your Desmos on your phone for free, which is always a good thing to do. So let's move on to the types of functions that we have. And this should be a review for most of us. Let's scroll back up here and clear this out. All right, so for most of us, we remember what we call the function machine. All right, we did that last year. It's kind of a little silly, I think, the way that this is just treated. So we have our x values here, and then we have our function machine, and then we have our y values. And basically what it's saying is that whatever, this is the function machine, whatever values you pick for y, go into the function machine, get calculated, and spits out a y value. This is basically your table, right? This is our table. So for instance, if we had 2, 4, and 7 in this function, and our function was x squared plus 5, right? 2 would go in. 2 times 2 is 4, plus 5, 9 would come out. So our point would be 2 and 9. 4 would go in. 4 times 4 is 16, plus 5, 21 would come out. So our point would be 4 and 21. 7 would go in. 7 times 7 is 49, plus 5, that'd be 54. 54 would come out. So our point would be 7 and 54. Right, so you kind of see how that works. It's just like our table. Our table is basically our function machine. Okay? So now there are a few different things that we have to think about in relationship to, does it work as a function? Just the illustration of this and seeing it and knowing how it works, how our table works, we can see that for every x that is put in, if it's a function, this is the function. If it's a function, it's going to spit out a y value. It just is. And it is possible for each unique x here, this x, it could go in and spit out the same y value. It's entirely possible. But every x value that you put in, the same x value, is going to be different from one another. All the x's are different. You can't duplicate here. It's just not possible. Duplicating here is not, if you put 4 in here and 4 in here, it's not going to give you 2 different y values. It's just not. Now, you could have some other type of situation that could, in a relation maybe, when there's a relationship, like there's a shape or something, but never in a function. The function is just, it's not going to work out that way. It isn't. You're going to put in a value for x, it's going to spit out a value for y. You put in the same value for x. Let's say I put in 4 again right here. It's still going to give me 21. This is not going to change, right? That's what it's saying. It's saying that for every value of x, the value for y is going to remain the same. You're not going to have 2 different values for y in a function. The same x is going to give you a different value for each one. All right? So you cannot have duplicate values here without duplicate values here. That is why we say that when we have an x here and a y here, let's say we have 4 and we have 2, and let's say we have a 3 here, it is possible for the different values of x to have the same y value, just depending on what the rest of this expression is. It's possible. So this would be a function. It is not possible, if this is x and this is y, to have the same values of x give you multiple values of y. It's just not possible. When you put 4 in here, it doesn't give you a different number over here, right? It's possible for 2 different numbers here to give you the same number here, but it is not possible for the same number plugged into the same function to give you 2 different values. It's just not possible that way. So this is not a function, this is a relation. The numbers are relative to one another. They're paired together and they're relative. So they are a relation, but they do not fulfill the function of this equation or this expression. Now, in order to have a relation, all the numbers must be related, all the x's must be related to a y. They have to be paired up. They have to be relative to another number. So this, when you have, let's say 4, 2, and 1 as your x values, and you only have 2 y values here, this one goes with this one goes with this one, and this one has no body, this is not a relation. It's not a function and it's not a relation, because in order for it to be a relation, all the numbers have to be related to another. They have to have a pairing up. There has to be a group of points. In order for there to be a group of points, then you have to have an x and a y, not an x by itself, not a y by itself. All right. So furthermore, every element of the range corresponds to no more than one member of the domain, because it has the property 1 to 1. So this here, let's put this back the way we had it. This here, where we had 7, and our result was 54. This is what we would call a 1-to-1 function, because for every x, there is a unique y. So this is a 1-to-1 function. And this is a standard and typical function. This is the one that we're going to see the most often. Think about our table. Whenever we calculate and create our points and know what to graph, every value of x that we choose gives us a unique value of y. That's your standard function 1-to-1. All right, this is neither a relation nor a function when there are not pairs. When there are pairs, when x is duplicated, it is a relation. And when we have unique x values but the same y values, that can be a function too. And the way that can be a function is when our function looks like this. Y is equal to positive 3. And that happens when we have y is equal to 0x plus 3. This is a function. But whatever we put in for x becomes a 0, so the answer is always 3. Right? So if we were to put 4 here, put 4, 0 times 4 is 0. 0 plus 3 is 3. We put 2 in for x. 0 times 2 is 0, plus 3 is still 3. So that is how we can have unique values for x, but still have the same y value, and then we end up with a horizontal line in that function. All right, so this is still a valid function, even though all of the y values are the same. A relation, we've already discussed, can't be the same because you can't put in, when you have x with more than one y, that can't be a function because every unique value of x is going to create a unique value of y in a function. It just is. I'm sorry. Every value of x is going to have a value of y. Now the y values might not be unique, but the x values will be unique. You're not going to take an x value, plug it into an equation, and get 2 different answers. That's what this is illustrating. So this is not a function at all. It's just a group of points that happen to be in a set together. It's not actually going through a function machine. All right. All right, so I hope that helped you clear that up, because in 21.9, we are going to decide whether these are functions or relations or neither, etc., and so on. So here's our first one. We have x value 4 and 3, and then we have a y value that is 3. Is this a function? Okay, I thought I would add that for fun, but it's kind of annoying. What is your answer? If you answered yes, this is a function, it equals a function, then you are correct. This is a function. All right, what about, let's say we have, for our x values, we have 7 and 5. And we have, for our y values, we have 3 and 4. And for 1 point, we have 7 and 3. And then for 1 point, we have 5 and 3. And for another point, we have 5 and 4. Is this a function? No, this is a relation. Because we have a unique x value. If we plug it into an expression, it's always going to give us that one answer back. It's not going to give us two different answers. So this is not a function, it is a relation. If you said no, it's a relation, then you are correct. All right, what about here? We have values of x. We have 4, we have 6, and we have 3. And our values of y, we have 4 goes with 5, 6 goes with 7, 3 has no partner. So is this a function? No. And it is not a function, and it is not a relation either. This is just something somebody threw together. We don't know what in the heck that is. All right, so let's look at something a little bit more difficult. Here, this is our values of x. X can be any real number, okay? And we plug it into a function machine. And that function machine is y equals x plus 2. And our y values are x plus 2. So is this one a function? If you said yes, it is a function, then you are correct. Because any number that we select for x, we'll plug it in and it will be this value, x plus 2. Right? It will have, so if we pick 3 for x, the y would be 5. If we pick 7 for x, the y would be 9. If we pick -2 for x, the y would be 0. So every x value would have a unique y value. So this would indeed become a function. And it would be a 1-to-1 function because every x value would have a unique y value because it has to solve an expression to get there. Right? And it's not going to give us two different ones. All right, bear with me, girls and boys. We are almost there. I know it's been almost an hour, but we have one more here. Let's do 21.10. We're just going to look at some sets here. I'm going to pause and type this up so I don't have to waste your time. All right, so here we have 21.10, and this is just a series of each 4 sets, and each set has 4 points. So based on the point values given, tell me whether or not A is a function. If you said yes, then you are correct. Yes, it is a function. And I don't know why I wrote the number 5. Guess because it starts with F. Why it is a function, yes, because each of these numbers here is different. And that's all we look at. What about B? Is this a function? If you said no, it is a relation, then you would be correct. Because we have the x value here and the x value here, they are duplicated and they have different y values. So because it's a duplicated point or x value with different y values, it cannot be a function, but it can be a relation because these are valid points and they can be put on the Cartesian coordinate system. All right, what about number 3? Is this a function? If you said yes, this is a function, then you are correct. Because even though we have this number here duplicated, this point is duplicated here, the y value that goes with it is exactly the same. So it is the effect of just calculating the same number twice and getting the same answer twice. We've just duplicated the point. We haven't created another value of y for that value of x. It is the same. It's just duplicated, but it's still a unique value of y for that value of x. So it is a function. Now what about D? Is D a function? Yes, D is a function because we have 1, 4, -1, and 3. Every point here has a unique x value. So it does not matter what the y value is. What matters is that each x is a unique value. So yes, this is a function also. All right. So we have one more thing to talk about, and that is the horizontal line test. And a horizontal line test is something that you can do visually to check and see if a graphed function or graphed line or shape or curve is indeed a function. So let's say we are given a graph that looks, I'm going to just kind of get close here. It looks a little bit like this. It goes like that, right? The horizontal line test says it asks us to check and see if it is a one-to-one function. A function is a one-to-one function provided that any horizontal line intersects its graph in at most one point. Okay. Now, we can't do the horizontal line test until after we do the vertical function test. So there's two tests. There's the vertical, which we know about. We did that last year. You have the vertical line test. The vertical line test tells us whether or not it's a function. That means as long as I can draw this line like this, and it only goes through the line of the graphed line in one point, then that is a function. Okay. Now I'm going to switch. Let me use my highlighter. That'll work. The horizontal line test, on the other hand, tells me whether or not it is a one-to-one function. So the horizontal line, I'm going to draw this way, parallel to the y-axis, hopefully. And as long as every place I draw that line, there's only one point where it crosses, then it is a one-to-one function. So one-to-one function, that is a check for that. All right, let's get another graph and see. Let me clear this. All right, so here is my graph. And I'm going to do a parabola, just because parabolas are fun. So here's my parabola. Excuse me. And I'm going to use the green to draw my vertical test. So here's my vertical line test. Draw on a series of lines. And there's only one point on each of these lines that crosses my parabola. So this is a function, right? But now I'm going to do my horizontal line test. And I'm going to start here. And it only takes me 2 lines to figure out that I can do 2 points on this horizontal line and 2 points on this horizontal line. So this is not nat. This is not a 1-to-1 function. Okay, so it is a function, but it's not a 1-to-1 function. The other one was a 1-to-1 function because it passed both the horizontal line and the vertical line, or the vertical line and the horizontal line. This one only passed the vertical line, so it's a function, but it's not a 1-to-1 function. Okay, so here are some examples that we might want to run through. So we have, let me pause and I'll draw them up here for you. All right, so here are 4 examples. This is 21.11, by the way. So I'm going to do the vertical line test first on this one. No. There's a point and a point and a point. So this is not a function. And actually what I'm going to do is I'm just going to go ahead and put in some little things right here. Function and 1-to-1. Function and 1-to-1. Function 1-to-1. Function 1. I guess I should make those arrows a little bit easier. 1-to-1. All right, so those are the questions we're asking ourselves. Is it a function or is it 1-to-1? This is not a function, so it can't be a 1-to-1 function, right? Okay, so if I draw my vertical line here, I only have 1 point of intersection here, 1 point of intersection here. So this looks like it's a function. So let's try the vertical line test, or the horizontal line test, sorry. 1 point of intersection, 1 point of intersection. So it looks like it's a 1-to-1 function as well. So let's try this one. All right, my vertical line test. So I have 1 point of intersection in all those. So let's try let's look here. So I have, this does not include, this does include, so I only have 1 point of intersection there. So on the vertical line test, this is indeed a function. But it is, we use 1 solid point, 1 open point, so whether or not the point is on the graph, the solid point indicates that the point is on the graph, and an open point, it's not on the graph. The graph is a function since every vertical line drawn intersects the graph in at most 1 point. It passes the vertical line test. But we know that the graph of a function may be broken, or as us mathematicians might say, discontinuous. It is not a 1-to-1 function because it does not pass the horizontal line test. And it does not pass the horizontal line test because of this. When we draw this line here and we draw this line here, we get multiple intersections here and multiple intersections here. So it's not 1-to-1. All right, same thing here. If we were to draw a line this way, it wouldn't be 1-to-1. So we know that's gone automatically. But is it a function? It is not a function because both of these circles are enclosed, which means the point is included, which means we got 2 points on a vertical line test, so it is not a function either. All right, so those are the different options that you see that we have. We see that a horizontal line on a Cartesian coordinate system is not a 1-to-1 function. And that also would tell me that a vertical line on a Cartesian coordinate system could not be a function in the first place because it's straight up and down. So it would have to be a line with a slope or a curve in order for it to be both. All right, and that is all we have for lesson 21. I know that was exceedingly long. But we had a long lesson to get through, and I will see you guys in lesson 22.